So today agenda for this webinar, so we'll be talking about some battery degradation mechanisms which are there. Okay, we'll see what lithium plating is. Generally, I'll talk more about this. Then we'll see how the C rate impacts the lithium plating. What is the correlation which is available by the research papers? And then we'll also see different charging algorithms which are available. We'll see impact of charging algorithm on lithium plating, different algorithms which are there. Then we see what is a trade-off between life and charging algorithm on lithium plating, right? We'll also see the simulation of CCCV algorithm and other algorithm which is called MSCC, multi-stage charging algorithm, or multi-stage constant current charging algorithm in the MATLAB. And Lokesh will take you through a live demo where he'll show how these algorithms are built in the Simulink environment and how you simulate these. And we will end the session with TechLine's overview. Just give me a second. Just give me a second. So today's speaker, me and Lokesh, both are there with you, and I think most of you know us very well. We both are co-founder of TechLens. We have more than now 11 experience in the EV industry. We both are IIT alumni. I am IIT Delhi alumni, and Lokesh is IIT Kharagpur alumni. We work with EV industry from last 11 years, working with Mahindra, Mercedes, Ather, ZF, right? All those companies we have worked in the past. So we bring a good amount of experience in terms of EVs, right? So I'll start with very complicated slide, which is right now I'm starting, right? Uh, Please don't unmute yourself at this point. Okay, yeah. So generally, this slide we cover after covering 4 hours of fundamentals and understanding on multiple things on battery chemistries and all. So directly at this point of time, I'm jumping over here because today's subject, our topic is our advanced topic. So I'm not going fundamental on batteries as of now and cells as of now because that's why I said it's an advanced topic today. And after 4 hours, when I brief about the cells and different mechanisms and all, I show the slides to our learners. But anyways, let's see this. So from the degradation perspective, the most common term which you might heard is your SCI growth, which is there, right? So which we call it loss of lithium inventory. And most commonly word which you have used is called lithium plating, right? You might have heard about this. And you might have heard about dendrite formations also, which is called lithium dendrite formation, which causes your short circuit thermal runaway and all those things, right? So somewhere, if you see this lithium plating, if we talk about only this today, we are not talking about anything else, right? So there are multiple mechanisms on anode side and cathode side. The loss of lithium inventory, loss of active cathode, lot of active anode, loss of electrolyte, right? Corrosion of collector, lithium plating, and all those mechanisms are there. But for this today's session, we'll only focus on lithium plating, which is there, right? And if you see the lithium plating, that depends on if you're charging your battery at high SOC, high rate discharge, charge and all, right? There are multiple mechanisms by which lithium plating happens. But before understanding that, okay, the lithium plating is happening by multiple reasons, let us understand what lithium plating is. Okay. So what happens if you ever heard about solvent shell, when the ions are passing from your cathode towards the anode, right? When they are traveling from the cathode towards the anode, there is a SCI layer, right? And this is called by solvent shell. So what happens during the desolvation process when the ion pass through the SCI layer, they in an ideal state scenario, they uniformly distribute in the graphite layers in case of my graphite anode, right? And they pass through the SCI layer. Please don't scribble on my screen, Mayur. Please don't scribble on my screen. I have to stop sharing now. Thank you very much. Please don't scribble on my screen. Okay. So what
Sorry sir,
happens?
गलती से हो गई.
No problem. So if you see this, the when the ions are passing in the your electrolyte, right? They are passing from cathode towards the anode during your charging process, right? So during the charging process, if you know that during the charging process only the ions travel from cathode to anode. And what happened? The solvent shell gets removed by this SCI layer and pure lithium ions intercalate. So intercalatism is a mechanism by the lithium ions travel in the graphite electrode. right? So this is called intercalation of the ions. In this process of intercalation, the lithium metals or lithium ion is removed from this solvent shell and they pass through it, right? So this is called solid state diffusion. So if you have attended our RC modeling classes, you might have understood there is something called diffusion and slow response mechanism, fast response mechanisms, right? Do you remember any one of you from the past webinars? Give me yes or no. We talked about it, diffusion mechanisms. We talked about fast uh, mechanism, we talked about slow mechanisms, right? Only one person remember this? Only Ian. Okay, Ian is messaging me directly. Okay, any which ways, if you have not remember, please go through the RC model. Chandan also remembers, great, right? So if you go through that, you will understand what is a slow response mechanism, what is fast response mechanism. So diffusion is always slower mechanism, right? Now let's see this. What happens when you are trying to charge at fast speed, right? At high C rate. So these lithium metals which are there, what happens when you're trying to charge at very fast C rate, right? They try to accumulate on the anode surface, right? Now imagine, let me give an example this with you, like plating. Have you heard about copper plating or anode plating or any kind of plating on a metal which is done by electrolyzing? So Praveen, don't scribble on my screen, please. Okay. So you have heard the chrome plating and all those things, right? So what they do, they try to dip an anode and cathode in a surface in a solution, and then there is a plating of metal, right? So how the plating of metal happens? Those ions, they try to deposit on a metal surface, on a particular surface, right? During the electrolysis process. The same kind of mechanism happens in the battery when you're trying to migrate ions, the lithium ions are very fast pace because at the end, this is metal, right? The lithium is also a metal. What happens when there is a crowded space in the anode, when all the ions are coming very close to each other, they try to make a what you call it bond with each other as a metal will bond I give an example to you the way the chrome plating happens on metal surfaces, right? Similar kind of mechanism here also happens where ions are trying to come together to each other to form a metal layer, which is called lithium plating, right? When you and this, if you see, is happening because you're trying to charge the battery at such a fast speed. There are other reasons also, the high temperature, low temperature, higher SOC. I'm only talking about today the charge rate, right? I'm not talking about the low temperature. And if you see, we talked about there are other mechanisms also, high charge, high SOC, cycling, non-uniform charging. So today's focus only for this webinar is the high DC charge, right? Now, what happens? These metal, when they come too close to, because understand this, we talked about in the RC modeling class also, the ions are big, right? They travel very slowly. This is diffusion mechanism which is happening because of concentration gradient. And when you're trying to bombard so many lithium ions at very fast pace, at a very given, very short duration of time, they combine with each other and form lithium metal, which is called lithium plating, right? Is this concept clear to all of you? Why the lithium plating is happening at the first place? Are you able to correlate with the understanding on chrome plating on the lithium metal plating, which happens on different metal? Is this clear to all of you? Why the plating is not happening, Yash, at slow charging speed? Because they're able to diffuse. Okay, understand this. Why the lithium ions are moving at the first place? They are moving because of concentration gradient, right? So lithium ions are there when you're charging the lithium ions. If you see that when the battery is fully discharged, all the lithium ions are there on the cathode side, okay, and very less amount of lithium ions are there on anode side. When you charge the battery pack, because of this gradient in the concentration, they diffuse, right? This is called diffusion of the ions and intercalation of the ions which are there. So when you try it at a slow process, the diffusion is very smooth. There is no issue at all. When you try to charge the battery pack at very fast pace, this solvent layer also breaks. Okay, because see what happens. This solvent layer prohibits all the ions to combine with each other while they are moving. When you're trying to move at such a fast pace, this solvent layer also breaks. and when metal to metal contact happens and they form a bond. Yes, is it clear to you? Right? Okay. Now let's see what happens. Let's see what happens at different charge rate, right? So if someone knows about half cell reactions and all those things, I'll not cover that today. There's something called lithium plating over potential. So typically the anode is supposed to be at zero voltage, right? If you know about standard electrode and all. I'm not going to cover this today because this is a very deep topic. Aren't we going to design graphite surface available according to Max? No. So Reshmi, understand this. That is how the LTO chemistry. You know that LTO is an anode. It's not a cathode chemistry, right? If you know about different uh, ions layers, which are the electrolyte layered architecture, polyanion, spinel, and all those things, you'll understand the 3D geometry of LTO is very good. So what happens? It allows at very fast pace of movement of those ions. And because that's a 3D geometry, graphite is a 2D kind of geometry, it's a layered geometry, right? So you can only move one by one. Imagine there is a two parallel plate and you're trying to insert a ball inside that, right? One by one. So that's that kind of mechanism. So when you talk about LTO, that's why the LTO supports you very high discharge or charge, very high charge rate specifically, right? Okay, not diluting the topic, coming back on this again. So if you see this, what happens? Okay. So if you see this, what happens? This is called lithium plating over potential. You're not supposed to go below zero because if you see the lithium electrode, when you're talking about lithium system, zero is my standard electrode potential for a half cell for a lithium metal, right? When you're trying to go below this, which is called the lithium plating, that means the lithium metals, the lithium ion will try to combine with each other and form the metal. If you go below zero, right? If you see this graph at 6C, if you see that particular 2C rating, you are just touching the border, right? Can you see this? When you're trying to increase the C rates for a given temperature, if you see this is going below this lithium plating potential. When you're trying to charge the battery at further higher speeds, which is 6C, you're further going below. So the more you are below zero, there is a higher chances of lithium plating. You want to avoid lithium plating, right? There is other example of temperature also. I showed you earlier, I told you earlier also. At lower temperature, the chances of lithium plating is high, which is shown by this graph also. If you see the 3C rating at 5 degree, you're getting much more lithium plating, right? And typically that's the reason also, if the C rate increase, what happened? The lithium plating will happen and dendrite formation will happen. Dendrite formation will lead to thermal runaway. Okay, I'll come back on that. And if you see one more thing, when the lithium plating is happening, and we'll talk about more about the cycles, it's not a constant phenomenon. What happens? The lithium plating potential, because of SCI layer formation cracking and consistent capacity loss and the aging of electrode materials and all those things. With respect to cycle, the lithium plating potential also comes down, right? So the same 1C rating, if you're continuously charging, right? After 525 cycle, the lithium potential becomes higher. It's very noteworthy to add that a new battery pack you can charge at faster speed, right? But an old battery pack you cannot charge at high C rates, right? See this example over here again. At 3C rating, when you're trying to charge the battery pack at 3C, if you see that initially for cycle 1, the issue was not so severe, right? Can you see this black color line? But if you see at the 325th cycle, this lithium potential is very high. So your charging algorithm cannot be remaining constant. It has to evolve with time also. If you're only designing for a charging algorithm for a fresh battery pack, you are going to create thermal runaway issues because of this, because the lithium plating potential is very high. Consider the fast charging and mega, like you know about CCS2 protocols. Now megawatt charging is also coming, right? If you are designing the battery pack charging algorithm based on the new battery pack, it's going to eventually fail in the field because you did not consider this scenario, how the lithium plating potential is changing with respect to time. Are you finding this insightful? Are you learned something new in this? Did you find this insightful? Help you understand this? Did you know this or this is something new for you? People be interactive. I want to interact with people. You know that if you attended my previous sessions. I want yes, no, are you learning? Are you finding it insightful? Only three people. Okay. So please interact, ask questions in the chat also if you're not unable to understand something, right? Okay, could I repeat the last part? No worries, let me repeat the last part again. So what I'm trying to tell you based on this graph, if you see this, can you see this black color line? Okay, let me slightly zoom in, no, for you. Let me make it sometime people join from the mobile also, right? Can you see this black color line? See, this is my lithium plating over potential. So you don't want to go below zero. The If you go to zero or below zero, the lithium plating happens, right? So metal to metal contact happen, the ions come too close to each other and form the metal. Now, if you see, and this 3C charging condition also, in the first cycle, that means when your battery pack is completely new, entirely new, the chances of lithium plating is comparatively lesser, right? So lithium plating will not be very severe. But if you see as a battery ages, so if you see this is cycle number graph. So this is cycle number 65, this blue color is cycle number 130, this is cycle number 325. After 300 cycles, see this lithium potential is extremely high. That means the same battery pack which was safe to charge at high C rate when the battery pack was new is not safe anymore when the battery pack is old. Are you understanding this? Are you understanding this thing? Right? This is something very, very important because mostly what happens when you're trying to, what happens because charging algorithm generally are not taken care by the battery people. There's a charger team sometimes gives it, right? But if they're not working together as a team, there is no collaboration. The charging team will tell, okay, I want to fast charge the battery pack, or the product planning team will tell, okay, I want to implement 150 or 250 kilowatt charging system, right? But what will happen if you're not considered these kind of scenarios in your simulation in advance? What will happen? Your eventually when your battery is old, right? After some time, maybe 2 years, 3 years down the line, thermal runaway scenarios will happen because there's something called dendrite formation. Okay. Let me slightly show you one thing. I think I've not covered that image. Okay. Generally I do in the class, but okay, because we don't want to go depth to it, but let me give you some because these people are. So what happens? There is your separator, right? So this is my anode, right? This is my anode. This is my separator, right? In between separator. And this is my cathode, correct? What happens when, as I told you, in this scenario, the lithium metals are trying to accumulate over here, right? So when they try to accumulate over here at this portion after the separator, they form needle-like structure. Because if you remember, have you seen a crystal structure, how they form? Crystalline. Have you ever seen how the crystals form of any metal, right? They are very sharp in nature, right? Same thing happens. The lithium metal, when they form or plating, they kind of make a needle-like structure on the anode surface. And this needle-like structure penetrate this separator. When this separator is penetrated by this needle-like structure, there is a short circuit which causes a thermal runaway in the battery packs. Okay, so this is something very important because eventually your lithium plating will form dendrites, which are needle-like structure, will break your separator and internal short circuit will happen and the thermal runaway will happen. So eventually it's very important for you to design the system such a way that your system is safe. And if you're not considering these kind of things and you don't have knowledge of all these things while designing the battery pack, eventually your system will fail in the field, right? After 1 year, 2 years, 3 years down the line. Okay, right. So let me talk about different charging algorithms which are there. So we have seen battery suppliers commit 5 to 6,000 cycle based on different chemistries. It can be a power cell, energy cell, and they don't commit you on 3C. Please always remember that. Whenever the site, and if you see this one more important thing, there's something called power cell and energy cell. Mostly you will find the power cell cycle life is very less, especially if you know about moly cells and all, right? Their cycle life is not so very high just because of the same reason, right? There is a multiple other things also, but for simplicity I'm telling you this. If you're trying to increase the C rate, right, eventually you're going to drop your life. see the classical example over here. Same battery pack, if you're charging at 1C, the lithium potential is not happening over here, right? But you're trying to charge at 3C, the lithium potential is hitting, no? Right? So the battery will age also early. Please understand this. So if you're trying to not, and if you heard about it, the fast charging destroys your battery pack eventually. You decrease your cycle life, right? Okay, coming back on this, the charging algorithm. So there are different charging algorithms which are available in the market. Okay, I'll answer all the question at the end. One second, let me just finish this. Okay, so if you see the most typical algorithm which are being used in the market, one is called CCCV, which is called constant current, constant voltage charging. Let me use a pointer again over here. So this is constant current, constant voltage charging. CPCV, where you give a constant power and then constant voltage charging. MCCCV, which is called constant current in multi-stages. And then CV, there's something called pulse charging. Then there's something called boost charging, and VCP, variable constant power charging, right? And actually this was the thing which I was trying to tell you in the previous case, right? So typically what happens, there are two kind of algorithm which is very famous. One is CCCV and pulse charging. Now, if you see, when you're trying to give a very high C rate for a very long period of time, as I told you, the same way the chrome plating happens on your metal, right? If you see the way you do the chrome plating or any kind of plating on your metals, same kind of things happens here also. When you're trying to give a constant current for a long period of time at very high C rate, all the lithium metals particles try to deposit on this. And can you see this surface? This is called plating, which happens on the anode surface. And but what happens if you try to give in between a gap? Can you see this very beautiful thing? In the constant CCCB charging, this force is very continuous. So there is a continuous potential difference. You're trying to give a very high current for a long period of time. And this was at 4C. But even if you're giving a 6C charging, but if you're giving intermediate gap, right? So what happens in this intermediate time, the ions has time to diffuse. Okay, so what happens? You given very fast charge and then you give an intermediate relaxation. The time was there for ions to diffuse, so they diffuse because this is your surface, right? This is your anode. The ions are supposed to diffuse inside this internally, right? So when you give a 1 second gap in between, the ions diffuse internally. And that is how the lithium plating does not happen. So if you see from the plating perspective, the pulse charging is better than constant current charging. Are you finding this insightful? Are you finding this useful? Is this something new you're learning? I want some at least 50, 60, 110 people are there, right? Okay, what is pulse charging? I have not covered it. Let me cover. So pulse charging, what you're trying to give is, you're trying to give a pulse of current. So in the constant CCCV charging, what you're doing, you're giving a constant current for a long period of time. Then you're giving like for up to 90% SOC level, you're giving constant current of 4C for suppose or 1C whatever, and then you're giving CV. Okay, in pulse charging, you don't give a constant current. You give in pulses. One pulse, then a break, then one pulse, then a break, then one pulse, then a break. Then you give a CV. In this method, when you give this intermediate relaxation, that time the battery is not charging, but that time diffusion is happening. That what limits the plating. So in this case, the plating is happening, but in this case, plating will not happen. Right? Okay, great. So from comparison perspective, I'll come back on this slide again. I'll hand over to Lokesh and he will show some simulations too at this point of time and show some other insights from the algorithm perspective. Lokesh, over to you. So meanwhile, are you people enjoying? Lokesh, are you there?
Yes, give me a few seconds, Vishal.
Yeah.
Am I audible and visible?
Yes, Lokesh, you are visible.
Okay, let me share my screen first. Yeah, is my screen visible?
Yeah.
Okay, so good evening, everyone, again. I think enough of this cell chemistry thing. While it's equally important, but let's park it for some time. Lithium plating, I think we have covered that concept, you know, quite in depth. Uh, Vishal has explained nicely. Let's try to understand charging from a different lens, from voltage, current, and temperature front. Okay, so fundamentally, what do we want in charging? So as a customer, I want two things only, right? One is I should be safe, right? My battery should not go into any crazy behavior, right? And second is my charging should be fast, right? Fundamentally, these two things only I want as a customer. So that surely as engineers we should address. But as engineers, there's one more thing which we address, or we give equal importance, and that is health of the battery. So as engineers, two things for us come from customers. One is safety, second is the charging time, and third, we ourselves take up that is SOH, because indirectly we are giving some warranty to the customers, right? So these are the three things which we care about as engineers when it comes to charging, developing charging algorithm, right? Um, Now, why do we have so many, type of algorithms? Why do we try so many things? Uh, Different cell chemistries are coming. B, different use cases are there. Drive cycles are there for, of the vehicles, the use cases of the battery. And see, we cannot control the discharging a lot, right? I mean, we define the boundaries when it comes to discharging of the battery, but it is up to the user, right? How he or she wants to use the battery or the vehicle, right? When it comes to charging, it is in our control, more or less, right? As long as we are addressing the two requirements of the customer, right? So, since charging the whole process, and that is half of the battery's usage, half is the other half is discharging, of course, is in our control. We try to maximize that, the opportunity, that control opportunity, and address the health part and safety and the charging time, right? So this slide is on the health, which I will come to it later. Before that, we'll go to paint screen. When people who attend the webinar know that I do things on whiteboard a bit old school way. So we'll understand again from current voltage, point of view, how things work. Okay. So, just one second. This bar, let me know. Yeah. See, so if we have a vehicle, I mean, let's say this is our uh, power point. We have our charger here, right? Charger is sitting here, and this would charge the battery, right? This battery again would be having BMS. I'll call this as BMS, and this would be battery, right? Remaining. Now, from voltage and current front, how things are working, we will see, through a graph. Let me take another color. So, what are the three requirements? One is safety. Second is charging time, and third is health part, right? And the reason, because of this health uh, optimization, we recommend not to do fast charging always, right? Because if we just do fast charging always, we would get, lesser charge, I mean, battery charge in lesser time, but then health would deteriorate, right? So how it works is like this. So to address safety, mainly when it comes to charging, we just want to ensure that the battery voltage doesn't exceed a certain limit. Okay, so we would have some maximum operating, value for the cells, right? So whatever is the number of series, number of cells in the series, we have the battery maximum voltage, right? So beyond that, we don't want battery to go. Okay, so this defines our safety limit. I mean, current values, upper limit of current, those things are also there, but this is fundamentally which we have to always keep in mind, that battery voltage should not exceed a limit. Okay, and that is how we address safety. When it comes to charging time, I'll take an analogy uh, for people who don't have any idea or more or less any idea on charging. I'll take this analogy. So let's say we have this water tank, okay, and I want to fill this. So I want to fill it through a tap, okay. So to fill it at uh, in least amount of time, what I would do is I would open it fully, right, 100%. So water would start filling in this tank, and of course there would be turbulence because the water is like flowing at uh, full flow rate. After a certain point, some water would start spilling over, right? And that would be the point where I would realize that I should be reducing the taps opening. So I would reduce it to 90, 80, 70, and then finally to zero. And that is how my finally water would the turbulence would reduce and water would fill fully, right? So if I see my flow rate of the water, it is fully open initially, and after certain point I would reduce it like this. Okay, this is an analogy only. It's not like exactly like this how charging works, but then similar, thought process is there when it comes to charging. Here it is water. The requirement is water should not spill over, right? I mean, uh, water spilling over is okay, but assume if it is, it was some inflammable, liquid, it would be risky, right? So in our case, it is battery voltage. So when we charge our battery, initially we pump good amount of current, and that is our CC value. We give CC value, constant current, and that is like considering the health part of the battery. We decide some current value, and we just give that constant current continuously. So the battery charges quickly, but once this criteria is met, we'll see how it meets. But then once this criteria is met, we go into safety mode. And that safety mode is called, we should maintain the voltage. We should not exceed the voltage beyond V max, battery voltage beyond V bat max, whatever you call it. And once you go in this mode, this is the behavior, behavior between charger and battery will go through the equation in some time. The current of the battery would automatically start reducing like this. Okay, so this phase where current is reducing like this is CV mode where we are maintaining the battery voltage, and this is CC mode. So this mode is for covering up that time for the fast charging, and this is for that final top up sort of, right? And most of the times this phase in public charger or home charger, this is between 80 to 90%. And this is the reason why most of the times we claim why what is the charging time for 0 to 80%, right? Because we know that 0 to 80% charging can be done fast, uh, but then the remaining it takes time, right? So when we claim charging time, we mostly do 0 to 80, 0 to 85%, because that is the phase where we can do CC charging. Okay, so I'll rub this part and what I can. So if we see voltage, how voltage increases with the current, uh, this is our time axis, this is voltage, and this is current. What I will do, this is current, this is voltage. Okay, so we're doing CC charging initially. It could be like this. At this point, we do CV, and then this is how CV ends. Okay. If we see battery voltage, first color should I take? I'll take this. Battery voltage would be some value. Let's say it's a 50 volt nominal system, so it would be somewhere around 40 volt here. It would charge. The battery voltage would increase like this. Okay, and if we see this point, this is the point where battery voltage would be at its maximum. Okay, okay, I should be saying it the other way. Sorry, please ignore the last 10 seconds. We'll start with charger voltage. So charger voltage would always have, some extra voltage between, from battery voltage. So it would be 40 plus some delta. Charger voltage would start like this. It would charge, and it is increasing because V of the charger is equal to V of the battery plus I into the drop. Okay, so the impedance drop. What is that impedance drop? This connection between charger and the battery, there would be an impedance drop. Okay, so there would be some losses through the line. Okay, so that would be I into impedance. That would be including wire losses. That would be including the harness inside the battery, and that would be also including the internal impedance of the battery. Okay, so three things: wire, harness inside the battery, and the impedance of the battery. Okay, all these three would lead to drop between voltage of the charger and the battery. Okay, so that would be maintained. Once charger reaches V bat max, what we do is we ask charger to go into CV mode. Okay, the control of CV is in the charger. So charger goes into CV mode, and when it goes into CV mode, battery voltage rises like this, and it goes closer to the charger voltage, and this is how it charges fully. Okay, so in this phase it is full current pumped in battery, so battery voltage is increasing like this. Okay, and battery voltage, since it is increasing with this current into impedance, the drop is there, so charger voltage has an offset over battery, and that is how charger voltage is increasing. Okay, once the charger voltage is at the V bat max value, what you do is the equation changes. Now current is not controlled. Initially in phase 1, current was controlled. In phase 2, voltage is controlled. Okay. So in phase 2, what happens? This equation is modified in this form: V charger minus V battery upon impedance would be equal to current. Okay, so now current is calculated based on this. Over here, charger voltage is changing based on this current, what we decide in CC mode. Okay, over here, current is calculated based on this equation. Okay, so is there any question?
No, no, okay, some disturbance I think was there from someone. They muted.
Okay, no problem. So this is how CCCV works. Now people have, since I told that we have charging only as an opportunity where we can fully control the dynamics of battery, the behavior, the health of the battery. We try to use this opportunity to max. So boost charging, one of the charging things. Profiles which Vishal showed, where we pump more charge initially, that opportunity is considered because lithium plating is not, it doesn't happen much relatively at lower SOCs, right? Similarly, MCC is done. What happens in MCC? You start with CC value, but at the end part, you start reducing the current like this. Okay. Vishal, can you help me with muting
Yes,
that
yes,
mic?
yes, yes. Please
Yeah,
go ahead, Lokesh. I'll remove the person.
thank you. So this is like how you reduce the CC reference values. What is the benefit of MCC? Again, as I said, it depends on the requirement. Here, one of the benefits, CC and CV both are happening in the charger, these algorithms. Now, by MCC, you have eliminated the need of CV, right? You are only changing the CC reference, and it is more or less like CV in sort of digital way. So your circuitry, which is required to do the CV control, you have the possibility to eliminate that. That is one. Other is, once you charge your battery, after a certain time, temperature would also increase, right? Would increase beyond certain, your reference threshold. So naturally, to address health, you would want to reduce the CC value so that at higher temperatures, the CC values are lesser. So it is one of the ways to optimize the charging in terms of the time and health of the battery. Okay, so again, MCC has its own reasons to do it too. I already told. Boost charging has its own reasons, so it depends on the requirement. If some battery is having active cooling on it, probably you would not care about the temperature based effect on the health. So it depends on what the requirement is, and what kind of battery it is, chemistry, and cooling wise and stuff. Okay, so fundamentally this is what is happening in terms of voltage and current. Okay, and current goes to zero when these two are equal, right? So the numerator becomes zero, the difference becomes zero, and current is zero, and that is how the current is finally zero. In practicality, like, you don't wait for zero, you just wait for something like around 0.5 or something. If the current is lesser than this, you stop charging. Okay. So yeah, in that case, when you don't wait for zero and you stop charging, if I zoom this part, this final thing, this brown curve, which is of battery voltage, would sort of settle down like this. And this is that RC behavior which we discuss in our other webinars. So, I mean, this is zoomed part. I mean, it would settle there only, more or less. Okay, so this is fundamentally what is happening in battery charging voltage and current wise. Okay, so now we will switch to Simulink window, MATLAB Simulink window, and we'll have a quick feel of how we implement the algorithm. And while I'll try to do few things from scratch, but time doesn't permit to do the whole simulation. So I already have model built with me. Okay, but before we do the model, we have to understand how we approach this modeling. Okay, so I'll just delete this part. When we do model thing, the intent is to you know develop charging algorithm which would sit you know uh, on some ECU, right? So battery is there, BMS is there, charger is there, right? And algo is there, right? Now we will follow this sort of architecture where charger is a physical thing, right? So you will keep it separate in your implementation. There would be one section which would mimic charger behavior. There would be one section which would mimic battery behavior, which would mimic BMS behavior, because in reality they are anywhere there, like physically, right? Algo we will keep, we will develop it separately, and then this part only, we generate code out of it and we put it on some ECU, right? Why do we do put this sort of architecture? For the modularity part. Tomorrow, if first day, if I am having CCCV algorithm and if I want to modify it to MCC algorithm, I just have to touch this block, okay, not the other blocks. They are just comfortably mimicking my charger hardware and my battery hardware. Okay, so in this way, there would be three sections where we would implement algo, charger, and battery respectively. So going to a Simulink window. So I've already done the implementation because time would not permit to do all the things from scratch. As I said, we would have our algorithm here. So I would just create one area here. We would have a charger behavior here. Okay, either you can make some element based circuit based charger, where actually how charger circuit looks like, you can mimic that, or you can make it through some equations. So different modeling approaches are there, right? Similar for battery RC model we cover in our webinars. You can take that, or you can take element based battery. Okay, for now I would take something called battery, which is in SimEscape library. Okay, so this battery which I have taken would mimic the battery behavior and also the BMS thing. So how BMS, if I double click it, um, sorry, I have taken out the battery. Yeah, so multiple battery locks are there. This makes more sense in this session. I mean, we cover these things in detail in our course, but can't do it now. So why I say that it does BMS thing also, because here the option is there to expose SOC measurement. That means SOC estimation is happening in this block, and that I mean basically happens in BMS. So since this block gives that option, that means it is having the BMS behavior also in it. So I am taking SOC out. These are the voltage terminals of the battery. Anything when you want to do, I mean, we're talking about voltage and current, so I mean, surely we want to measure voltage and current. So I would take voltage sensor and I would take current sensor, right? I'll not be doing the whole implementation. It would take too much time. 1 hour is not enough, but I'll do as much as possible for the field part. Okay. So my battery is here. And my voltage measurement, current measurement is here. Okay. SOC, why I'm taking it here is based on the SOC, I would decide when to charge the battery. Okay, instead of manually doing it, I would decide based on SOC. Now, once I have this, I would put my charging algorithm here. Uh, One of the more popular ways to do it is using state flow. Why state flow? Because when it comes to charging, the steps are more digital, right? You just go from one state, CC state, to CV stage, or if it is boost, there is one boost stage, then there is regular CC, then there is CV stage. So it makes more sense to do charging algorithm in state flow, but you're not like limited by this. You can do it in using blocks and other ways also. Okay, and some sort of charger circuitry would be required here. So um, I would be taking some comparisons and PID controller here. Okay. So what this PID controller would do, it would maintain the current. Okay. Sorry, it would maintain the voltage for CV. And for CC, I need to give some constant current, right? So what I would be doing, I would be taking some current value, which would be coming from this block, and then that would go to the battery. Okay, so people who are not, or who are not, understanding it completely, please wait for a few minutes. You will understand what we are finally implementing. Okay, so a switch would compare the voltage V bat max I talked about, right? So if the voltage of the battery, which we would get from here, right? So these are some implementation requirements, these blocks. The measuring voltage of the battery. Once the voltage of the battery, is equal to the reference V bat max, which we talked about. So I would call it V bat max, and this variable I can define, in my M script or somewhere. Once this thing is there, the current which should be going to the battery should be going through this PID. That means it would go into CV mode, right? So how this that means is the current line, correct? So and this should be going to the battery. So I need current source, which would feed current to the battery. One second. Yeah. So this block would, would do the current pumping to the battery. Okay, it can be either through CC or CV mode. Okay, so this is for the CV, that how much current should be going. So PID would decide that. Okay, this is one of the ways. You can do it through other ways, through circuit and other things also. Okay, this is the CC line. So for now, I mean, I would just take a constant, whatever CC current I decide, I can put it here. Okay, so some variable I define here. Okay, so CC current would go here. Once the voltage of the battery is greater than my VBAT max, whatever the maximum battery voltage I want, the CV would start working, right? Now these two things right now, I mean, they are, very basic. Whatever algo we want to do, charging, discharging, we would do it here, and the output from this state flow would command these CCCV logics. Okay, and that is what I have implemented here in the blocks on the left side. Okay, so I mean, we don't have time to implement the whole circuit here. Okay, so I would directly jump into this. Yeah, I guess it's totally not required right now. So yeah, you see, this is a battery. This is voltage measurement. This is a current source. Okay, SOC I'm taking out. What I've defined here is if SOC is less than 30%, I would start charging. If SOC is 100%, I would enable discharging so that the charging, discharging, both the phases can be seen here. Okay, this trigger is activating the switch. Okay, so charging would happen when SOC is less than 30. So this would become one, this line, and this charging line would get activated. Discharging is this line, okay, which is again coming from the state flow block. Okay, so discharging is this line, which is discharging the battery through the current source. And when the SOC is less than 30%, I would activate this port of the switch, and that is the charging part. Okay, so we saw this port is CC charging value, right, which again comes from the state flow, and this port is CV charging port where PID controller would control the CV mode, and the equation which we saw for CV, the current would be reducing in that way, the CV, how it works in CV. Okay, so now what we have done here is we have clearly, at one place developed battery model. Clearly, the charger model is here. As I said, we can have charger circuit also. This is one way to mimic the charger behavior. Okay, and our algorithm is developed in this state flow. Now, whatever thing you want to do in the algorithm, you can do here. This is a very basic implementation. But then, if you want to increase the number of CC, stages here, all you have to do is CC1 is here. You can add CC2. You can define the values of CC2 stage. So it initializes, and then it works like this. Okay, multiple CC stages would be there. So, and here also I have neatly put the charging part on one side and the charging behavior on one side, right? So uh, this way that modularity is there. So whenever I want to change anything in the charging, I can change it on, one section of the implementation, and other part is not disturbed. Okay, so if I run the model, what is this? One second, guys. Okay, this implementations. So if you see the plots, when SOC is 1, that means 100%, the discharging phase is working. Okay, so the current is minus 10 amperes. I've defined it as minus 10. So constant minus 10 ampere discharge I'm doing, and SOC is reducing like this. Okay, that SOC estimation is happening in the battery block itself. Okay, that's not of our concern right now. Charging algorithm is what we are trying to implement. So we'll see that part, and that's how we have put it in state 4 separately. Okay. So once it touches 30%, the hysteresis block which we have used, that would trigger the charging uh, stage. Okay, so SOC is increasing because now CC charging has started. I have given 15 ampere reference, and once the VVBAT max reference which I have given, that reference is equal to the battery voltage. It goes into CV mode, and that's how the voltage of the battery, sorry, the charger is maintained at 4.2, and the charging continues to 100%. So that 0 to 80% charging time claim which I told about, you can see it here also. Till around 70-80% charging, it's quite linear and quite fast. The last part takes more or less same time, the last 20% of charging. So that's how we, when it comes to claiming the charging time, we claim 0 to 80% or so. Okay. I have implemented MCC also. The intent of implementing this is to show that how at one place only we can just, modify the things. You want to do boost charging, you can add more things here and not disturb the other part of your simulation. So I've just created one more CC. I changed the reference value of CC, and it would just, it has already run. So here the MCC is changing. Once my whatever reference logic is met for MCC, the second CC phase is starting. If you want more CC, you can do. Here still CV is happening, right? As I told, if you just want to completely eliminate the voltage control circuitry in your charger, you can just have multiple CCs. If I Okay, let me just take a new snapshot. This is last thing from my side anyway.
Today, Lokesh,
So,
you also today all the fun you are having today.
uh,
Huh?
yeah, a few
So
more minutes only.
core forte of Lokesh today is reflecting in the session today. Okay, go ahead, Lokesh.
Yeah, the last thing, Vishal, I know we are exceeding time. So what I'm saying is, if you want to, avoid the circuitry of voltage control, what you can do is you can do multiple CCs, and this is how you would just do CC and more or less mimic the CV charging, right? If you just want to dominate the time, here you would be losing some time. What you can do is with the due required safety margins, you can do it like this so that you would not be, reducing the time. Instead, would be increasing only. If you just want to match the time, initially you can do this, and later when the voltages are closer, you can do on the lower side. Okay, so MCC can be done in many ways. Again, it depends on the requirement. Okay, so now coming to the slide. Um, Fun fact, I have made this slide only. Rest slides which are there, which Vishal explained, was made by Vishal. So I mostly spend time in on whiteboard, the white paint screen. So coming to this slide, as the health deteriorates with aging, the impedance of the battery increases, right? So naturally, we saw that because of impedance, the CV phase is triggered, right? So once impedance increases, the CV part triggers earlier. Okay. So because of that, the constant current duration reduces. Okay. That is one thing where you have to act based on the health. Vice versa also can be done. Uh, Once you know how charging affects the health, you can modify your charging, and that is how these many charging algorithms are there. You modify your charging so that you control the health of the battery in terms of its impedance, in terms of its capacity. Okay, so they are interrelated. It's sort of chicken egg story. You control charging to optimize the health change would control the charging behavior, and charging would change. Okay, so this is what I wanted to sort of explain through this slide. And quickly checking, I think that's all from my side. Vishal, over to you.
Yeah, Lokesh, the final conclusion part is still not covered. Let me cover that also quickly. So
Sure.
Lokesh, this is what happens when you have 12 years experience only in doing algorithm. You go in the flow of can you stop sharing? I'll share my
Yeah,
screen.
yeah. How do I stop sharing? Have I
Mm,
stopped?
Nope.
Yeah, now I have.
Yeah. So, and so day in, day out, Lokesh has taken the breath on the algorithms from last 12 years, right? So this is what happens. So when he talks about algorithms, he get emotional. Okay, I'll talk about the different algorithms and their impact on plating, charging time, and performance. Yeah, before that, I'll just cover what TechLens is. Right, I'll give a brief introduction about TechLens. I think most of you know about it already, but let me quickly cover. So we have a EV ecosystem, we have training programs, we provide engineering services also, and then we are startup of government recognized startup in India. We both, as I already mentioned, have good experience in the industry, me and Lokesh both, and we are a team of 20 people, only technical people who are building new things, right? We